So we're going to start with some audience questions. So any questions do we have the microphones?
Hello?
Hello.
Hi, my question is for Matthew. With the birds and the black wings, do you think that flight efficiency is the most important factor acting on that? Or do you think that thermal regulation of extremities is also important? And and also like if there's differences in where you find these birds climate-wise?
All good questions, and they're always it's biology, so there are always going to be every feature of the organism is going to have multiple functions, and whether the thermal regulation is important. I hadn't thought about that as much, but it's if the wings are, I could see it being important certainly. But we haven't measured anything about how it might impact thermal regulation, so I can't say very much about that. We looked at in our analyses. We also looked at climate, whether that affected whether the birds evolved darkly colored wings or not. For one, it's difficult to say because when you're an albatross and you fly thousands of miles in a year, like what is your habitat, right? It could be, it could vary. It could have, there's extreme variation in their habitat from week to week. That's difficult to say. But when we did manage to nail it down, we included that in our analyses, and it didn't seem like climate was that important. It seemed like the wing loading was the more important variable. The thermal regulation is also a really potentially important one.
Additional questions?
Hi, great talks. I have 3 questions. The first one, very quickly, is for Alan. Have you considered the emissivity of your material in your temperature measurements? And the last 2 questions are for Matthew. Have you considered the thermal properties of melanin itself? How good it is in dissipating heat in your calculation, and also how do you know the blue pigment that you see is actually DHN melanin?
Okay. Hello.
What?
So I can answer if I'm. So we have looked at emissivities, which transmission, reflection, absorptance add up to 1. So in our case, the emissivity is quite minimal. And it's, I think there's a line. I think there's often a convolution of emissivity, transmittance, and reflectance. But I think there's an important distinction to be made where emissivity and absorptance is more along the lines of what happens with dyes and visible color, whereas transmittance and reflectance, at least in the infrared, is more along the lines of what you get with structural coloration. So our effects, because we're changing microstructure, are mostly structural, and there is a contribution from emissivity, but it's relatively small for these materials. Although if we put a heat source in there, then that contribution, will be dominant. So.
Okay. So thanks. So the diffuse. So we haven't. Our measurements of. We basically have measured the thermal properties in terms of heating, and then heats, and then cooling down. There's a variation in both of those. I don't know if does that answer your question? Yeah, I mean we considered both heating up and cooling down in our, there's I guess I focused mostly on the heating up aspect of it here. There's also important variation in the cooling down aspect. How we know that it's DHN melanin? Well, it's a controlled synthesis. We haven't done NMR or anything like that on it yet to definitively show it, but it's those colors all the color variation is based on concentration, And as you get more and more concentrated, you ultimately, and actually I have some in my bag I can show you later, but it's black. So yeah, and it goes, at high concentrations, it becomes exactly what you would expect from any other melanin. So it seems to be a concentration effect, and we think it has something weird in the surface chemistry that's causing it to form these structural colors in solution. But we're fairly, the reaction is fairly straightforward, and we're fairly confident that it's DHN, but yeah, of course it needs to be definitively shown.
Thank you. Very nice talks, and I have a question for Matthew again. I'm fascinated by your research with the black in the wings and how it could have implications for other species. And I'm interested also in, have you done any studies with black juxtaposed to white in the wings? Because you're getting different thermal properties that might generate more energy, but also the connection to recent discovery with monarchs and the black band around the outside of the monarch wing. They've recently found out, I think it's theory at this point, but they're investigating that the monarchs that travel the furthest have more white spots in the black band. And again, you've got that black-white contrast. So I'm just curious if you have any comments about that.
Yeah, we've thought about, why, if it's such if it's so important for flight efficiency, why are there so many species that just have the tips black? Why are there many birds that just have the, half of it black, half of it white? Again, it comes back to trade-offs, and thermoregulation might be important. We also know, and this is why, we've, when we got this, we were like, why aren't they doing this? Why aren't they doing this with planes? It seems like it was a fairly, as we're biologists and we figured this out, why haven't they started doing it? And the reason, of course, is that the fuel is stored in the wings, and you don't want to heat up that's one reason at least. You don't want to heat up the wings too much for obvious reasons. Thermal properties can be important. We also know that melanin is important. So maybe some birds don't want their wings to get too hot. So there may be a trade-off there, and they put it only where it's going to have the most effects. Very efficient in their use of melanin. So like on the trailing edges, on the tips of wings, where there's going to be the most turbulence. Does that answer your question? Sorry. Yeah. Okay. Yeah. So there are trade-offs, and I haven't heard about that monarch research, but it sounds really interesting.
So I see Peter wants to ask a question, so I want to keep this relatively quick, but I got two questions. One is, about the silkworm cocoons, and I truly don't know. Does the silkworm wrap that cocoon starting at the outside and work its way in? And because everything that you showed as when you were making your cylinders, you start at the inside and work your way out, and I don't know which is that a factor. The other one has to do with the birds and the melanin. So that's a second question. You've kind of focused on seabirds, and their ability to soar and stay aloft for long periods of time. We have another bird that is on a completely other end of the spectrum, and you talked about it very briefly. Are hummingbirds. They basically soar zero, but yet they migrate thousands of miles each year. And how does that compare or work into your theory that about thermal heating? Because it doesn't seem to be a factor at all. So you guys can take those two questions however you like.
Sure. Okay, I'll start with the silkworm. So what we were going after is the end result, and no matter how the silkworm does it, the things that I did not show today that I couldn't necessarily show are the two other ways that we're going about this. Instead of just filament winding from the interior and out, we're also looking at a novel approach using electrospinning from the melt. So the electrospinning would give us more of that non-woven effect, more of the effect that looks like the cocoon, And the other thing that we're doing in terms of hydrogen storage is, if you're familiar with metal organic frameworks, we are developing new metal organic frameworks that we can include in the tank itself. So this would give us more of that inside out structure and getting as much insulation and as much hydrogen storage as we can. So we're trying to take the approach of using as many different materials in the structure as we can, rather than trying to mimic, how it's being built.
And can I ask a question?
Sure.
Yeah, so I saw the gloves, and I saw that they had a fire retardant effect. But so do they have? What's the thermal effect, or is there a thermoregulatory effect of the gloves beyond that, or
Yeah, there is. So the thermal arrays that we developed for the firefighter gloves, it was really the Department of Homeland Security was looking for gloves and for personnel protective equipment that was less bulky, so that when they're going in a life and death situation, they can get in and out quickly, they can move, they're not overburdened, they're not overheated. With the gloves in particular, firefighters, we were trying to develop a firefighter glove that you can go to lunch with a firefighter and they can eat, they can use their hands. Oftentimes they're going to open a door and they don't even have the dexterity to do that. So a lot of the research that we did went into the design on how we were going to build the thermal array and where does it go. So what you don't see in that glove are the different heights and the different aspect ratios and the different cup. There's an actual cup in that thermal array. So that standoff siloxane composite material has a wall thickness, a height, and then we also have double-sided materials. So in the back of the hand, there's a certain height of the cup, and then in between the fingers, there's a different cup height. So there's a lot of different design aspects that go into the material beyond the material, but the shape is really, really important.
Okay, cool. I think you had a second, and I've already forgotten the second question. It was, hummingbirds, right? Hummingbirds are incredible, we haven't, they're not seabirds, so we haven't analyzed them, and we haven't, like I said, we haven't tried to see if our results extend to flapping flight. And hummingbirds also, you probably also know that they have a really weird flying style, so they're not just flapping their wings, they're actually kind of moving them in figure eights. Our pigeon bot would have to have another, a hummingbird bot would have to have additional layers of complexity on top of that to figure them out. Hummingbirds, one thing I will say is that they do have, they're extremely iridescent, and actually their iridescence is on their wings. And like I said, iridescent feathers actually heat up more than dark feathers. So yeah, you could argue that they're actually taking this thermal effect to an extreme, in that, now they have these really hot feathers. But I don't buy that myself, so I wouldn't argue that. But I would really have to look and see if the color effect holds for flapping flight, and then if it holds for this really weird hummingbird style flight. Hummingbirds just, I mean, they're only eating sugar, so they're just they're powered through pure anger and sugar. So to make it across, yeah.
So we have an online question, and I see you. So online question.
Yes, thank you. The online question is for Dr. Jen Lally, and this person is interested in whether Nanosonic has made some significant progress, not just in the thermal properties for hydrogen storage, but also in the leak-proof properties for hydrogen storage. And they were referencing back to the X-33 program of NASA from several years ago, and was wondering if you had an update on progress there.
Yes. Yeah. So the big issue with hydrogen storage is coming at it from replacing metals. So what happens with metals is that they undergo hydrogen embrittlement and catastrophic failure. So as you have a tank that's based on metal, you'll have hydrogen ingress, and then once it starts to expand, there's no going back. You get this explosive failure, which is obviously not good. In terms of the materials that we've been developing for the cryo tanks, we are really looking at the differences in free volume that we can control within the polymer morphology. So if we can control the free volume within the polymer, then we can make a material that will allow for more of a viscoelastic response to the hydrogen. So the big advantages that we've looked at recently, we're going beyond just that core that we were looking at, and now introducing this like an aerogel wrap around it to give us that extra insulation. And then the final wrap that we've got is the filament wound structures. So the big advantage there now is really this introduction of the new aerogel wrappable layer. So that's been the latest.
Oh, no. Tap on power. But there's a follow-up? One follow-up. Is that okay? Sure. Sorry.
And one follow-up to that is just how biodegradable are the products that you're working with now? And are you thinking about that closed loop of zero waste?
Yes. So we do not have, everything that we have in-house at this point is not biodegradable, but we'd love to get there. I mean, we were joking at lunch, I'd like to be able to eat the fork, eat the utensils. But what we've got in-house right now is we do have, as I mentioned, the very facile, benign process, and I can't get the details, but it's essentially based on vinegar. So we can break down a lot of different epoxy B-stage materials, which are just your expired systems. We can also break down the thermosets when we add some additional materials. In terms of the closed loop, we also have a solvent recovery system. So in addition to reclaiming the fibers, we can then also reclaim those solvents. One of the innovations that we had recently, though, in terms of reclaiming the fibers, is if we use a very robust packaging system on the outside of the composites and you soak that material and wash that, you can actually retain the initial weave and retain the length and the orientation of the toes or the woven composites, which is great because we've really focused on the carbon fiber composites because that's so much of that is going to the landfill. So that's something that we feel if we can somehow find a way to use the carbon fiber, not just in a chopped form, if we can retain those filaments to reuse in filament winding or to reuse the weaves and get us something, it might not be a life-critical application, but if we can reuse those materials, we've kind of gotten half the battle of recycling. So in terms of the other materials that we're looking at, Dr. Bump had mentioned the enzymatic degumming of the hemp, where a lot of the manufacturing in terms of long staple hemp production, that's not done here. So if we can look at strengthening the hemp fibers to get that strength that we'd like through the long staple materials, that's something else that we can look at. So we don't have everything in a closed loop yet, but we're pushing everything in that direction.
Thank you, sir.
Thanks. This is a pretty simple question, I think. It's for Alon. One thing that it seemed surprising is the change from 0 to 50% transmissivity when you stretch the fabric. It seems like the area was way less, that the area that you were revealing was way less than 50% of the area. Is that just, do you know what I mean? So like you stretch the fabric and you have gaps now where you can get the transmission. It seemed like that was way less than 50%, but you're getting 50% loss. Does that just work a different way, or is that a trick with how I'm seeing the image?
So there's two things there. So one is typically when we show the SEM images, they're only for 0, 30, 50% strain, just so you can, clearly see it. And the maximum 50% loss or change in transmittance or reflectance, I think it's actually about 45, comes out at 100% strain. So you can map the fractional area change along with the Young's modulus, and it will and the infrared transmittance or reflectance changes, and they'll exactly track the Young's modulus curve. So basically, it's determined by the mechanical properties of the polymer. So it's pretty consistent. I think it's just maybe our maximum values at 100% strain, but our images where we're showing the change, and it's just simply an experimental limitation, which actually one of my other students overcame recently, where we're showing the change is only for 10, 30, 50% strain. So that's just the difference. But those aerial changes match exactly what you see it. 30 and 50% strain. So that's a great question.
Any other questions from the audience or the other panelists? Okay, so I have one last question. So a lot of and this is for all of the panelists, and you can choose to answer or not.
No.
So a lot of these systems, a lot of these natural structures are extremely complex, heterogeneous, multi-scale, and they're created under benign conditions, right? That we do not fully understand. And so my question is twofold. One is, do you feel stymied sometimes by modern manufacturing processes being insufficient to actually mimic these structures in the complexity that they exist in nature, or is that a future you problem? And have you started from a sustainability perspective looked at, or is the community at large really looking at how these things are fabricated in vivo, and ways that we can then transform our own manufacturing processes to leverage that?
I'll answer the first part of that.
Sure.
In terms of being limited by manufacturing processes, when we're looking at some of the siloxane high temperature materials, and if you're looking at a polymer-derived ceramic, that thermal exposure that the material is being exposed to actually helps it. So even though you're processing it closer to room temperature, when it's being put in the environment where it's going to see that harsh atmosphere, that atmosphere actually helps post-process it, which is really cool. One of the things that we saw recently too is that we're doing a lot of EMI shielding. So the concrete yesterday that we saw was just awesome in the room. We've got a material where we've been looking at directed energy exposure and high energy laser exposure, and found that when certain materials are exposed to certain levels of energy deposition, you'll see a phase change as a function of that. So sometimes it's not just the manufacturing process that you're limited to, but it's also thinking about what the material might be exposed to and how that can assist you where it is a problem, but how do you turn that problem into something that's a hypothesis and a discovery?
Yeah, it's a feature, not a bug.
Yeah. Yeah.
I can weigh in on those too. Hopefully I'm not interrupting Matt. But so there's a really good point about the complexity of biological systems that is far more than what you have in a standard system. And I look at this from very much the perspective of an engineer, where we try to figure out the key concept that gives you, not the majority, but let's say essential functionality for any biological system, and then to distill that concept and almost reverse engineer it and improve upon it and introduce it into an artificial system. So I wouldn't say that it's necessarily stymieing, because, capturing the complexity of biology, I think, is with any practical technology is not pragmatic from my perspective. I just think we can't understand all the things that are happening in a biological system. So that's kind of the take on it. I guess a good way to look at it will be to say, you have this biological system, and it's got all these bells and whistles, and you understand how the engine works. Like if you compare it to a car, you understand the wheels. You understand the windows, you understand how the seats work. And what we're doing is essentially saying, well, this car is a big box and it's got 4 round things at the bottom of it, and that's how we're going to treat it. So that's the sophistication that we use compared to what's happening in biology. For the sustainability perspective, there's a lot of lessons to be learned from biology. For us, we just look at it from what's a sustainability approach that's pragmatic technologically that we can incorporate in what we're doing. And a good example of that, in the food packaging paper, we started using essentially the same type of SCBS rubber that you have in adult incontinence diapers, or rubber grips on toothbrushes, which are thrown away, and waste copper that you find in copper pipes, which are also thrown away. So you can literally take the materials that we're using, get them and get them from a garbage dump as disposable things, and just strip off toothbrushes and make our materials. So we don't necessarily draw from biology. We think about it from the perspective of what's practical from a manufacturing standpoint. So.
Yeah, and I think your system is much more complex than our system in some ways because it's dynamic. They're moving parts all the time that are enabling this incredible color change and thermal change and everything else. So yeah, I think you've done a great job of focusing on one part and saying this, separating it out, looking at it piecemeal and saying, okay, I can't replicate this whole system, but I can at least look at one part and see if I can replicate that part. And then, maybe in the future, add color, add rippling. I don't know what your plans are, but yeah, I think that's I love the squids as well. But it's just too much, like too much for my brain to think about all those things happening. So I was happy looking at a dead feather, dead static system, and even that turns out to be incredibly complex. And in terms of the manufacturing processes, I'll focus on the biological manufacturing processes because those are really annoying because they seem very simple, but then when you try to replicate them, it's extremely difficult. So we'll start with the materials. So the two materials that are in our system are keratin and melanin. And so, we looked, okay, the melanin has tons of interesting properties. Let's look at that, and see if we can work with that before we start thinking about keratin. And then, we get with keratin, with melanin, and it's an insoluble, heavily polymerized material. As you said, we still don't know the chemical structure of it. It's hard to work with. When we started, it was very hard to get large amounts of it. You would spend a week and you would wind up with a microgram of material from, if you try to extract it from a feather, you'd have to use like a ton of, of chicken feathers or something else. And then you go through this incredibly long-term reaction, and then you'd wind up with a tiny little amount that still had a bunch of keratin on it. Then we spent a long time, we said, okay, we'll cheat a little bit and make synthetic melanin, and that's, that wound up working quite well. But then, now we're kind of moving further away from the natural system. I'll also say, that we still, melanin, we're treating it as just a simple polymer, but it also has lipids and proteins associated with it that also have critical properties that I don't think any of us have really thought about, or have thought about, but haven't done anything about. So, and then we get into keratin, and now we're trying to move into studying keratin, and that's also incredibly hard to work with. It's not very soluble. We have to use HI. What is it? One of the worst, most difficult. No, not hydrofluoric acid, but HISP. That one, yes. So it's, biology does it extremely easily. So then we have another material where we've tried to, that's based on keratin and air, and we couldn't use real keratin, so we wound up using a polymer, and we got, we kind of verified that you can make this color using just by self-assembly. But it's not biological. It's with the plastic, with a synthetic polymer. We have to heat it to 100 degrees C to stop the reaction. I'd say the biological systems of manufacture are still incredibly frustrating, but still hold a ton of potential. If we can get these things to work at room temperature with organic materials, it would be a huge breakthrough, and we're still working towards it.
Maybe Alexander can look at it in the future.
If I could weigh in, melanin, I will say, I think you're underselling the difficulty of synthesizing melanin and the beautiful work you guys.
I'm not a chemist, so
it is the single most complicated biopolymer there is. Chemistry does just crazy things chemically. So that me, your work on that is the most beautiful example of, actually finding reasonable small building blocks where you can recapitulate the properties of melanin. And that's something people have been trying to do for, more than 50 years, right? And thinking about that. So that's a really, really elegant example, because it's just, the most difficult to work with polymer that I know of. And that's
and we make a stripped down, like you make a stripped down version of it that we can play with. And
Alexander, you're going to say from the student perspective.
Oh, yeah. I just wanted to say that sometimes the stuff are overwhelming from the nature, and from some animals, the inspiration can be never-ending story. We can have
security.
Exactly. Yeah, but it's good to have like simple view on some aspects and create some simpler version, simpler idea, taking two small, like simple components and designing some great material. It has so many functionalities.
Fantastic. Thank you. Any last go rounds? Yeah. No, we don't have time. I'm told we don't have time. Well, I'd like to thank the panelists on my panel. That was really fantastic. Thank you.